Eric Isaacs, President of the Carnegie Institution for Science. It's my pleasure to welcome you today to this Kavli Prize and Carnegie Lecture. We are really deeply honored to join the Kavli Foundation, the Royal Embassy of Norway, and the Norwegian Academy of Science and Letters in presenting the Kavli Prize Lecture. Today, we're particularly proud to welcome Dr. Ewine van Dishoeck, who is a pioneering astrochemist, professor of molecular astrophysics at the University of Leiden in the Netherlands. Her work extends across all three of the Kavli categories you just heard about: the very big, the very small, and the very complex. Dr. van Dishoeck's research looks at the molecules of organic material that float through the clouds and through interstellar space. These molecules are created by stars and serve as the building blocks for new celestial objects, including galaxies, stars, and planets. Her research combines radio observations, laboratory simulations, and theoretical chemistry to form a better understanding of how these clouds and molecules can evolve into planet-forming disks. Dr. van Dishoeck's work has deep implications for one of the most exciting aspects of astronomy today, where she can shed light on the origins and evolution of the thousands of discovered planets circling around stars not too distant from our own sun. Dr. van Dishoeck brings exceptional qualifications to this potentially transformational question. She earned her PhD in astrophysics at the Leiden University, and after pursuing research in the United States at Harvard, Caltech, and Princeton, she then returned back to Leiden as a professor in 1980. She's also renowned as a scientific leader, which is with a great talent for building international consensus necessary to launch big collaborative projects. She's currently the president of the International Astronomical Union, an organization that promotes international cooperation on all aspects of the science of astronomy. And she's also the director of the Netherlands Research School for Astronomy. Importantly, she played a decisive role in founding the Atacama Large Millimeter Array, or ALMA, in Chile, which is considered one of the truly first international astronomical observatories, sitting at about 15 or 16,000 feet in the high Chilean desert. Dr. van Dishoeck is a foreign associate of the U.S. National Academy of Sciences, and she has received many awards and honors, including the Albert Einstein World Award for Science, the James Craig Watson Medal in 2018, and now, of course, the Kavli Prize in Astrophysics. Today, she'll be joined by Emmy Award-winning journalist Frank Sesno, who is the Director of Strategic Initiatives at the George Washington University School of Media and Public Affairs. I know you all are eager to hear this fascinating conversation. So please join me in welcoming Dr. Ewine van Dishoeck and Mr. Frank Sesno. Thank you.
Well, thank you very much, Eric, for that wonderful introduction. And Ewine van Dishoeck, welcome to you.
Well, welcome, and welcome to all the people that are listening here. Good afternoon, good evening, good morning, wherever you are. It's great to see so many of you here on the line.
It is great to see as many as we have joining. I'm sorry that we're not in person. We're in my house and yours, I think, in very different places. This is a result of the COVID problem that we've got, the pandemic. But what a great time to be speaking with you. And you know, you at a time of COVID and pandemic and politics and all the rest, you have this great line that you said when you accepted the James Craig Watson Medal. You said, through astronomy, we can remind people that we are all world citizens on a small, fragile planet under the same beautiful sky. And so I think you're going to inspire us here tonight.
I hope so. I hope to bring you a little bit of perspective.
Before we get to that, I think it would be fun for people to know a little bit about you. You're a very active person. You've been engaged in the sciences since you were a young student, first with chemistry and then into this. And you're a very active outdoors person, and you come to the United States when you can, pretty much every summer, if I'm not mistaken. Tell people about yourself.
Yeah, indeed. I mean, for the last 40 years, every summer, except this summer, we have been coming to the western part of the US and going camping there in the Eastern Sierras and the Grand Tetons, just to be outdoors and to see the beautiful nature. So that has been one of our biggest joys always in life, to go there.
And you're a kayaker, as I understand. There's a water connection there.
Well, yes, I was looking indeed at the pictures of Fred Kavli on the lake, and basically being in a kayak on the lake, it is first of all inspirational because of the beauty of the nature around you, but it's also it links sort of with the science that I'm doing. The water that's there, where does that water come from? The pebbles, the rocks, they are the building blocks of our planets, of other planets. Snow, ice, the snow lines play a role in the science that I do. So whenever I sit there in this little boat, it's also inspirational for the kind of science that I'm doing.
So let's get to it. Now, to the audience, here's what we're going to do in our conversation. We're going to turn to you periodically and we'll ask you a question. And we'll look for your answer. And I think Ewine will have some interesting responses to that, and then we'll work from there. We'll also be taking your questions, as you know, through the chat function. And in a little bit later, I'll put some of your questions to her as well. So with your indulgence, let's start with our first question to you, which will launch our conversation. And it's a pretty simple one. We'll put it up. Have you ever looked through a telescope? Straightforward, yes or no. You can answer this right on your screen there, if it's a touch screen or if you're using a mouse, and we'll see your answers very quickly. I suspect this will be a bit of an unusual crowd, but be honest, these are anonymous ballots. Ewine, I'm sure you've met plenty of people who've looked through and not looked through telescopes in your talk.
Exactly.
All right, well, let's see what we've got here in just a minute. I'm anxious to see this. While we do this, though, Ewine, let me ask you, when did you first look through a telescope?
Well, that's a good question. I think I must have been around 7 years old. Then one of my girlfriends in elementary school, her father was actually an astronomy professor who lived near the big telescopes, then the big telescopes in Leiden. And so we had birthday parties there. And so I think that is when I first looked through a telescope there and saw the moons of.
And were you captivated instantly?
Sorry?
Were you captivated instantly?
Yes. But I must say the full love for astronomy came only when I saw the beautiful night sky, which we will see in a moment.
Let's see if we have results. Okay, 92% have looked through a telescope. Is that about what you would expect? Is that what you hear?
Yeah, it's about there. Yes, it's good.
All right, so let me turn it over to you now for a few minutes. And why don't you start your talk? And what we'll do is we're going to kind of weave in and out of these things with a bit of background on the origins, our origins in space.
Yes. Okay. So again, welcome to everybody. It's great if you are just joining here. We're getting started, and what I'm going to tell you in the next sort of 7-8 minutes is a little bit of our story as to where we come from. I said already, astronomy provides perspective, and this is one of the beautiful pictures of the night sky, the kind of pictures that also inspired, I think, Fred Kavli when he was looking near his mountain home at the sky and got also this inspiration. But our story, actually, our origins started in these dark clouds that you see here in the beautiful Milky Way around it. This is where, in such a dark cloud, that's where our solar system was actually born. So if we now turn the Milky Way as such that we could actually look at it from above, then it would look as follows. So first we were looking at it from the side, but now this is in an artist impression, but with real astronomical data included. That is what our Milky Way would actually look like. You see here the center of the Milky Way, where we now know that there is a big black hole, massive black hole there. But for the rest, we see here the sort of 250 billion stars. The size here is about 50,000 light years. And our sun is just one of those few hundred billion stars in the Milky Way. And so we really live on this small rocky planet around a quite ordinary star somewhere in the outskirts of our galaxy. So that is one part of the perspective to give you. Now, one of the most exciting developments in astronomy has undoubtedly been the discovery of planets around other stars. Centuries and centuries speculations about it, but the firm scientific proof did not come until 1995, and that led actually to the Nobel Prize in 2019. We now know through various ground-based and space-based observations that actually planets around other stars are common. On average, about every star has one planet. But in this zoo of planets, there is a type that is actually a little bit different from that what we have in our own solar systems. You know, some of them are like Jupiter or like Saturn, some of them are like Earth, but there is also a family of planets, mostly super Earths and mini Neptunes, somewhere between 1 and 10 times the mass of the Earth, that has no equivalent in our own solar system. So that actually brings and that raises quite a number of age-old questions, namely not just what is their composition, could they be habitable, but also, you know, what sets sort of this diversity of planets that we see around other stars. And directly linked to that is also the question, actually, how we on, as our Earth, our solar system was formed some 4.5 billion years ago. And we're getting some exciting new results from that. Actually, just a few days ago, the OSIRIS-REx mission touched down on asteroid Bennett that you see over here, and it sampled some of that material from it, and it's going to bring it back to Earth. There's also a Japanese mission, Hayabusa, that did on another asteroid a couple of years ago. And that is actually going to tell us something about the material out of which we being our Earth is built. This is telling us something about the inner solar system. Now, we also have sort of comets in the outer solar system. These are made not just of rock that you see over there, but also of ice, a mixture of rock and ice. And they have been preserved in deep cold for the last sort of 4.5 billion years. And in 2014, the Rosetta mission actually landed for the first time on such a comet and actually sniffed sort of the gases around them. So where does this all start? So if we were in the audience, I would now ask you which constellation is this? So I'll give you 2 seconds, and of course it's Orion. But what you see here is lots of stars. But what we have learned is actually that the space between these stars is not empty, but it's filled with a very, very, very dilute gas. And the denser regions of that gas are actually called clouds. And the Orion Nebula that you see here in the Sword of Orion is one such example of a dark cloud where at the moment actually new stars and planets are being built. So let's look here. This is a little movie from based on astronomical data from the Hubble Space Telescopes, where we see these clouds now as silhouettes against a dark background. And if I would put my telescope on one of these dark clouds here, that's where I would see new stars and planets being formed. And that is basically where we would see a very rich chemistry. And these clouds are so dark because they contain tiny little dust particles. Think of silicons, think of sand on the beach, but then a lot smaller, only thousandths of a millimeter in diameter. But they do the scattering, the absorption and the scattering that makes it dark, just like little smoke particles make a sort of an atmosphere look dark. So we form stars in these dark clouds, but because of rotation, also there is a disk that forms around these stars, and that's where you build actually the planets. And you can see that here in this little animation where we have a planet that actually can clear a gap actually in this cloud. Whoops, that happened here. Okay, sorry. Oops. Apologies for that. So here is actually where we have sort of this disk in which new planets can actually form. Now, can we see this? That was an animation. And yes, with the new facilities that we have, like ALMA, we actually now see sort of these regions in which new planets are likely forming here in these images. And we see them actually on the scale of our own solar system. And this is not just one image. That was the first image that ALMA took in 2015, but now we have whole galleries of these ALMA images showing these intriguing structures on the scales of solar systems that are likely indicative of the regions in which new planets are being formed actually at this moment. So what is actually happening here? Here is a little animation that we have one of these planet-forming disks. And it consists of these tiny dust particles. They can collide with each other. They can grow to larger and larger particles. And that is what we see here. Here we see them in the disk, and then we see them colliding with each other. Sometimes they stick, sometimes they don't stick. But if they stick, they grow larger and larger bodies. So just like Bedu that we saw just shortly ago, and you see sort of this rubble pile of planetesimals actually being built here. So those are the building blocks out of which new planetary systems can be made. So to summarize this part, we have now found that nearly all young stars are surrounded by these disks thanks to ALMA. The sizes of them are comparable to our own solar system. The masses are enough to form planets, and the structures in these disks now point to planet formation in action. In other words, the ingredients for planet formation are quite common, actually.
Wow, that's amazing and beautiful and humbling and all of that. How, you say, we can start to see these planets forming? What time frame are we talking about here?
Yeah, so that's a good question, because our Earth formed already some 4.5 billion years ago. But on astronomical timescales, sort of star and planet formation goes pretty quickly, only timescales of a few million years. So that's nothing on astronomical timescales. So we have to catch them at the right moment.
How do you as an astronomer track that, right? I mean, you're looking at moments in time, a day, a week, a month, 10 years across millions of years.
Yeah. That's so. So obviously we cannot wait for a million years, but we do that through statistics, actually. So we take different classes of objects, and then through statistics we can determine lifetimes, and we can see how they change actually over lifetimes.
Let me come back to
we are lucky that there are phenomena that are on time scales of only 10 years, but that's very rare.
It's sort of, this is where the theoretical comes in, of course, obviously.
Yeah.
But let me come back and ask you about the OSIRIS-REx and the mission that you mentioned there. But as you said, it happened just a few days ago. I mean, that's news. That's exciting. And there was one very excited story that I pulled for this. Very breathless headline: NASA spacecraft touches asteroid 200 billion miles from Earth. And it said, if successful, the mission would be the first time NASA has ever taken a sample from one of the estimated 1 million asteroids in our solar system, which scientists believe could shed light on how the universe was formed and how water ended up on Earth. Now, there have been other missions. I know you've mentioned this to me. How excited are you about this? How important is this in your work? Because this is some of what you do.
Well, I think what Bennu is sampling at this very moment and bringing back to Earth is some of the raw materials, these sort of planetesimals, these building blocks out of which the Earth was made. So it is a carbon-rich object. So it has organic material. It has some water, likely. That means that we can also look at what we call the isotopic ratios, the heavy water, actually, that is there. The ratio of heavy water to normal water tells us something about the origin of where it came from, the water. And of course, bringing it back to Earth, that's the special thing here, is that on Earth we have laboratories with instruments that we can really study this material in details. When you go to distant objects, you can do some remote sensing, but there's nothing like bringing it back to Earth and then using the most sophisticated instruments that we have in laboratories on Earth to investigate.
Which will be done in this case in just a few years. Okay, let's go back to telescopes for a minute. And our next polling question for our wonderful audience, which now exceeds 600 people. So let's put this next question up. Speaking of telescopes, how many of you own a telescope? Do you actually have one? It's in your living room, it's in your den, it's aimed up the window. This is just sort of a sort of simple question. While we're waiting for the responses of Ina, when did you get your first telescope?
I'm not sure I have one myself. That's very fortunate to be able to use some of the most sophisticated ones.
I remember getting one as a small, I think I was probably 10 or 12 years old, and it was this little thing on a little tripod, and I think I used it to look at the moon. That was probably all it was good for, but it was fun. Well, okay, so about a third of people have a telescope, 2/3 don't. So if someone doesn't have a telescope, is there any way they can go and borrow one?
I think the best way would be to go to one of the amateur telescopes. So there are quite a number of observatories, yes, that are available and where you can go and especially go to open nights. Most observatories, also the professional observatories, have viewing evenings maybe once a month or something like that, and that is just fantastic to be there.
So let me turn it back then to you on the subject of telescopes and sort of big telescopes and really big collaborations that have led to ALMA and some of these other things, and invite you to take us there.
Yeah. All right, good. So let's go a little bit to how we actually do it all. So here is the cloud out of which the stars and planets form. Here is a simulated disk, and it would be wonderful if you could study this disk and observe it if it were as big as this on the sky. But that's not. I mean, why do we always need telescopes that go deeper and that look sharper? And that's because this tiny little disk is so small on the sky that we really needed a new generation of telescopes to be able to zoom in there on such a planet-forming disk. Now, one of the telescopes that I've used most now in my career is ALMA. And ALMA is the first actually worldwide collaboration in astronomy. And I was fortunate to be part of the group of people that actually helped to bring these different partners together, both in the US, and led here from the National Radio Astronomy Observatory, the European Southern Observatory in Europe, and then East Asia, and that is represented by the NUAJ in Tokyo. And together, these partners have actually put an array of some 66 telescopes, millimeter wavelengths, on a high altitude plane in northern Chile. And you see that over here, and it was inaugurated around 2013. Now, where are we actually? We are in northern Chile. So this is on the border actually between Bolivia, Argentina, and Chile, near the little town of San Pedro de Atacama. And here you see even the New York Times has a travel guide on this, and it says, why did we go there? Actually, truly high and dry. That's what we needed for our observations. Now you see here also the, what is it? The mule and the car. That's of course not what we're using here. We are at this place, but we have a more sophisticated truck actually to drive our telescopes up the mountain to 5,000 meters that you see indicated here. So ALMA is also actually a testimony to high-tech technology, and you have to also think of the logistics, getting all the parts to build these 66 telescopes from 3 different continents, to get those all to northern Chile, then to assemble them at a sort of an altitude, to mid-level altitude at 3,000 meters, where you can still think, and you can test them. And then once they are assembled and tested, then they go on this high altitude. Then they go on this big truck, and then they are driven into an array at 5,000 meters, where they are used for astronomical observations. Now, behind each of these antennas, behind of each of these radio dishes, which operate at millimeter wavelengths, are the eyes and ears of ALMA. And here you see the eyes. Those are the receivers, very sensitive. This is actually where some of the nanotechnology comes in. Devices actually that work really at the quantum limits to capture these very, very weak astronomical signals. So here is actually where you see ALMA, as it was nearly completed, and every time I'm there at 5,000 meters, it's both literally but also figuratively a breathtaking experience to be there. So here's actually where you see ALMA in operational. So rather than having a single dish, the signals of all of these 66 antennas are actually correlated with each other, connected with each other. And in that way, we are able to get a much sharper image than we would be able to get with a single dish. We're basically able to simulate a telescope with a diameter of up to 16 kilometers. These dishes can be put at distances of up to 16 kilometers away from each other, and that we get a very sharp image, like the images that I showed you of those planets forming disks. And here we see again the beautiful sky with the Magellanic Clouds rising there, and you see basically, ALMA dancing there in the night.
I want to ask you one quick question about this. You had a very significant role in making this happen, and because you really worked to persuade a lot of scientists from different nations from all around the world to actually work together, which is no mean feat, as I understand it, with scientists.
Well, there were a lot of people, of course, helping there, but I had the advantage that I was actually closely connected to the US.
Well, one of your colleagues described you as very persuasive and positive.
Thank you very much.
Was it very difficult to bring the scientists together to move to this?
Yes and no. I think all the three continents started with their own projects, but when they realized that by putting it together, we could make an even more powerful array, because the sort of the science quality goes not with n, the number of antennas, but with n squared. Then everybody realized this was a win-win situation for everybody to put it all together and make one array that was going to be much more powerful than any of the continents could afford themselves.
So not only are you a brilliant scientist, hence the Kavli Prize and other recognition, but you're a very persuasive person as well. So now let's connect the origins of our world with the way we look at it with your real focus, which is, well, one of them anyway, but by way of this next polling question. Let's put up the next question. Do you think there is life elsewhere in the universe? And we'll ask you to sort of rate this. Yes, you're absolutely sure there is life. No, not sure, but probably. Pretty unlikely, or no, not a chance. And this is very interesting because, you know, this is sort of what you're, I don't know, Ewine, are you looking for life out there?
Not myself yet, but in a second I'll say a little bit more about that. Yes, I'm actually very interested to see what the answer is going to be on this.
You're certainly looking for the building blocks, right?
Definitely, we're going to talk about the building blocks.
We will talk about the building blocks. Let's see if we've got any responses yet from the poll. Have we got? Okay, so 50% yes, absolutely. 45% not sure, but probably. So that's 95% think there's, you know, probably or definitely life out there. And nobody says not a chance. Now, it just so happens, by the way, there was an actual scientific poll of Americans that was conducted. I don't know if you saw this, an Ipsos poll just earlier this year. 57% of the respondents said not only do they think there's life, they think there's intelligent life out there. What's your response?
Well, I think what the response is going to be that sort of the next generation of telescopes are going to be able to actually answer that question. It's of course been a question that has been with us for centuries, but I think we are actually the first generation of scientists that has the technology now available to able to answer this question scientifically. Of course, at the moment, we don't know. I will show that the building blocks are going to be widely spread, so that the building blocks are going to be available. But of course, at the moment, we don't have any proof yet. But these two telescopes, the James Webb Space Telescopes, which will be launched in 2021, and also the extremely large telescopes, and then the first one coming online is the European ELT in 2027, they actually have the capabilities to start searching for the composition in of biomarkers, so to say, in the atmospheres of planets, also Earth-like planets, maybe super Earth-like planets, and then sort of the next generation that comes after that may be even more powerful in space. So I think we are actually in a very interesting point in time that we're be able to start to answer this question.
So where there's smoke, there's fire, and presumably
yes.
water, there's life. So let me ask you to take us there and talk to us about
yeah, let me talk then a little bit about the smoke that leads to the fire. So where does it all start? It starts with the simplest building blocks, namely the elements. Hydrogen, helium, they come from the Big Bang, the start of the universe. But the elements that we actually have in our bodies, the carbon, nitrogen, oxygen, they are much less in terms of numbers than hydrogen. But they were made actually a little bit later through the first and the second and the third generations of stars, that actually made them through nuclear fusion in their interiors and then returned them to the interstellar medium, the clouds basically between the stars, out of which the next generation of stars and planets then forms. So this is what we actually have available. We have mostly hydrogen, and then just a tiny little bit of carbon, nitrogen, and oxygen. So chemists used to say, don't even bother looking for molecules. It's so cold, so empty there. You will not find any molecules. But then, fortunately, the astronomers started tuning their receivers, and lo and behold, they did find molecules. Water was one of the first ones detected already in 1969. And we detect them actually through their signals, their spectral signals that they have. Every molecule, basically, thanks to the laws of quantum mechanics, tumbles in space in a very characteristic way. And that means that every molecule has sort of a fingerprint with which we can identify it uniquely, both on Earth and in space. And so we found actually a whole zoo of molecules in these kinds of clouds between the stars. Here you see just a few of them. You see methanol, which is a very abundant molecule, ethylene glycol, methyl cyanide, ethanol, actually, in case you're wondering. A cloud like this would have about enough alcohol to probably fill about 10 to the 27 bottles of whiskey there. Also more complex polycyclic aromatic hydrocarbons as a class, as a family of molecules is out there. But also there are some molecules that we haven't found yet. Everybody always asks, how about the simplest amino acids? Glycine has not yet been firmly identified in interstellar clouds. And this is another little molecule that may not be so necessary for the origin of life, but is certainly necessary for the maintenance of life. This is actually caffeine that you see over there. But the point is that these molecules that have not yet been detected are not that much more complex than the ones that we've seen already. So with the new facilities like ALMA, we can go a lot deeper than we have been able to go so far. Now, how do we think that these molecules are made? Well, it starts actually in these very cold clouds, even prior to collapse of the cloud to form a new young star. Here you see a little animation that is actually based on the laboratory experiments that we did in Leiden and also elsewhere in the world. Once a day, a hydrogen atom lands on one of these small dust grains. It finds an oxygen. It can make, there we go. There we actually are making molecular oxygen. There we are making hydrogen peroxide. Yeah, and now we're actually going to make 2 water molecules. So this is maybe a few days, and now we go and speed up to 10,000 or 100,000 years, and now we make a whole ice mantle actually on one of these dust grains. And in fact, if we go to these cold clouds, we find that most of the oxygen is actually, a significant fraction of it has been turned into this water ice. So most of the water that actually eventually ends up in the oceans on Earth, in the lakes on which we were kayaking, was actually formed in the cloud out of which our solar system formed. And as one of my colleagues put it, that actually means that water is older than the sun itself. nice to think about that.
Water is older than the sun, 4.5.
Yeah. So to summarize, what have we learned? We have learned that these interstellar clouds, even though they are cold and tenuous, actually have a very rich chemical composition. We see water, we see complex organic molecules, we see them around the majority of the forming stars throughout actually the Milky Way. So these building blocks at least are common. And if we look at the composition, then again, will they end up as the building blocks of new planets? Well, if we think of comets as one of the building blocks of planets, then there is a large similarity there in the composition. So this is then the sort of the second message, is that also these building blocks are quite widespread.
So Ewine, a question, and I know you've been asked this a lot. I think it would be very interesting for this group. How then did the Earth end up so wet compared to its planetary neighbors, Venus and Mars, that didn't?
Yeah, so, well, that's actually a good question. So first of all, the Earth has 70% of it is covered by water. So we think we are actually on a wet planet, but we're not that wet. We're actually relatively dry. If you would bring all of the water together, maybe it's not much more than, say, the state of Colorado. And also Venus and Mars, indeed, they look very dry now, but they may have been formed actually with the same amount of water or very comparable amount of water as our own Earth. They just evolved very differently. Of course, Venus got into a runaway greenhouse effect with the high concentrations of CO2 in its atmosphere. And Mars is actually a very low mass planet, and it basically lost a large part of its water in that way. So fortunately, Earth was able to hold on to a significant fraction of it, and that is why we now actually have such a beautiful blue planet.
But as you're looking at other solar systems and where these situations may replicate, that band, that place where that planet would need to be, how do you look for that? What are you seeing?
Yeah, so we're looking actually for when water can actually be liquid. So the planet needs to be at the right place from the parent star, not too close, that's too hot, not too far away, then it's too cold, then everything will be ice. So we're looking for planets that are in the so-called habitable zone. So that is an important element. But whether or not they are water rich, that also depends a little bit on sort of the dynamics in that young planetary system. And we know that some of these water rich planetesimals building blocks were actually scattered from the outer solar system into the inner solar system where Earth was formed, and brought some of that water there. So it also depends on maybe whether there has another giant planet already formed that can sort of shape then the water content of the inner planets.
So do you think there's another watery planet out there? And back to that earlier question, do you think that there is life out there?
I'm in the sort of the second category, in the sense that it's we still need to prove it, but it is certainly very likely that that's going to be there. But also, again, a warning that when we talk about life, it can be all kinds of different forms of life. Of course, we can talk about very simple forms of life, single cellular life, which we know formed very quickly on the young Earth. Whereas multicellular life took a long time to develop on Earth. So there is also sort of a difference what you're talking about there.
So we have a lot of questions from the audience, and I want to get to them. But first, our last question, which takes us back to what you talked about earlier. When you looked at that sky, that's when you were hooked. So it's a little different kind of question here. Have you ever drawn or taken a picture of the night sky? You know, we've all been out there, stared up at the Milky Way on some beautiful, perfectly dark night, or seen the shooting stars which capture our imagination. For those fortunate enough to travel and to capture the moment, the Northern Lights, right? These brilliant, beautiful displays. So our fourth question to you, have you ever drawn or taken a picture of the night sky? Ewine, you like the night sky?
Oh, yes, definitely. So inspirational.
What's your favorite? Do you have a favorite night sky view?
Well, I mean, if I think the southern sky is really gorgeous. That's more beautiful than the northern sky is. Even that's.
Let's see if we've got responses from people if they've. So, wow,
Yeah.
3/4 of the folks have taken a picture or drawn the night sky. And this is a setup because you and I talked, full disclosure, that you have not only a science eye, but you have an artistic eye. So I will turn it over to you to tell us where you.
Yes, yes, yeah. So, what is my favorite picture? So, I mean, obviously, looking at the real sky, but I also, like sort of the combination of astronomy and art, because it's not just us that scientists that are inspired by the beautiful night sky, but you see it's basically throughout culture, whether it's poetry, whether it's music, whether it is here paintings as we have here, and of course being Dutch, we have the Starry Night from Vincent van Gogh. One of them that you see over here is the Big Dipper in there, but you can go to any place in the world and you will find some inspiration there. Here is one of my favorites from Australia, actually, from the Aboriginals. They have the beautiful southern sky above them. And in fact, the Milky Way dreaming, that is a part of their cosmology, the way of their society, basically part of their society. And you see here the Seven Sisters, actually, with Orion here in this beautiful painting. Again, other part of the world, if you look here at the right, the Pacific Northwest, Canada, the story about how first Raven put the sun actually on the firmament. And then here we go more to the Expressionists, Stars by Kandinsky, picture that I like very much also because even though clouds were not known yet at the time that he was painting it, this looks just like the stars being born here in a dark cloud. So I like this painting also a lot. And then this is really my favorite. It's actually in our collection. It's an English engraving that dates from 1798. And it's so appropriate to this whole subject now, because they already speculated about these other planetary systems. The center is our own solar system, known at that time with 7 planets. But he speculated already that there could be other solar systems. Some of them with more planets, some of them with less, some of them closer by, some of them further in. And that's exactly what we are observing now, with this whole large variety of exoplanets. So here you see it. I mean, this is probably my favorite. My favorite picture.
That's great. It's great. Let's go to the audience questions now, and we'll go through them as quickly as we can. We got more than 24 of them, so I'll throw them at you quickly and see what you can do. First one, please define nebula.
Yes, a cloud, I would say, sort of basically a somewhat denser concentration of the gas in interstellar space, the space between the stars.
And you can
see the Orion Nebula is because it looks nebulous, so to say. That's how the word was first coined.
Well, so the next question actually specifically asks: Are there known protoplanetary disks in the Orion Nebula?
Yes, there are, and they are actually called proplets. That was a name again that was coined early on. But yes, they were provided actually some of the first evidence, even before ALMA, that there were these disks around young stars. You could see them either as silhouette against the bright background, or you could see them basically through their emission.
Niels asks, why isn't all the material in a new solar system contained within the star, given its large mass compared to everything else?
Mm-hmm. Well, a large part actually of the cloud, when it collapses, actually goes into the young star that builds the star. But about 1% of the mass, because the cloud literally rotates, ends up in this rotating disk around the star. That's basically the conservation of angular momentum, and that's where a small fraction of the material ends up. So So yeah, the bulk goes into the star, but a small fraction.
Here's one back to the night sky again. Someone asks, can we see gas in space, like in the Orion Nebula, in the visible night sky?
Well, indeed, I think the Orion Nebula is visible at night with a small binoculars even. So you don't need a powerful telescope to see that. The Andromeda Nebula, that's a different type of nebula. That's actually a whole galaxy. So that was the confusion about a century ago. Are all these nebulae the same? And some of them are the nebula, the clouds that I talked about that form stars. Others are actually entire galaxies, like, for example, also the Magellanic clouds that we saw in this movie with coming by with the ALMA dance.
Stuart's got a good question. How many observations go into the kind of statistical analysis of star and planet formation that you talked about?
That's a very good question. As many as we can get, but so obviously the statistical significance increases with the number of objects. At the moment, we're still at, we started sort of with dozens, now we are at a few hundreds. We are ramping up to a few thousands, but sort of that is the numbers that you should be thinking about.
Andreas asked this one, how long after the sun ignited, his air quotes, did it take for the planets to coalesce into a form recognizable to us?
Oh, that's a very good question. Yes. Actually, as the protostar, as we say, as it evolves, it initially sort of doesn't have the nuclear fusion yet. That has not yet ignited. That only happens after a few million years. But actually, even before then, we see already planets forming. So there have just been, only a couple of years ago, the first firm detection of young planets actually in such a planet-forming disk, at a stage that the young star was only sort of barely starting to ignite, not even hydrogen yet, but deuterium.
You're asked by another attendee, could asteroids continue to attract materials and ultimately form a planet?
If they are not too much stirred up, so again, a very good question. I think we have the asteroid belt between Mars and Jupiter, and that contains a lot of these building blocks, but they're continuously being perturbed, so to say, by the presence of Jupiter. If they were in a more sort of quiescent place, then as long as they are able to collide with each other, then yes, they could still grow.
So Lee says, how does water continue to exist on objects in the vacuum of space? Lee says it should have boiled off long ago.
It will sublimate, yes, definitely. Well, boil is depends, of course, also how hot it is or how warm it is. It's pretty cold out there in space, so a lot of it can continue to exist as ice, but some of it will sublimate, and especially if you think of any of these bodies that come close to the sun in their sort of passage through the solar system, then they will start to sublimate quite a lot of material. But there is underneath is quite a bit of a reservoir that then comes back, that then comes to the surface. So you maintain a lot of it actually below the surface.
Abina, we may come out of this event and you're going to have a lot of competition here because the number of people are asking telescope questions. Don asks, and maybe you know and maybe you don't, how do I use a community telescope online? Are there online telescopes and tools? Andreas, by the way, just to cluster these things here a little bit, points out that in Southern California, the Orange County astronomers have a telescope loaner program and outreach to schools, and you can find that at ocastronomers.org.
Yeah.
Are you familiar with other online tools and telescopes?
Yeah, well, I mean, actually, I think Las Cumbres Observatory in observatories in the southern southwestern US, is a wonderful facility. Has lots of programs for schools to look through the telescopes. You use them also robotic. I mean, many of these telescopes are now robotic. You can, you don't even have to go there, but you can even have some of them do robotic observations. So yeah, I think there are many good opportunities there. And sometimes, I mean, when I'm in the Grand Tetons, I mean, people put up small telescopes there, and they have then sort of evenings there that you can look at telescopes viewing. So
I want to thank everybody for sending in their questions. I wish we had more time. We'd get to all of them, but I do want to give you an opportunity before we conclude here to share some thoughts that you may have from your perspective, having won the Kavli Prize, seeing what's happening in science now, thinking about what it takes to invest in young scientists, and I know you're very interested in young women in the sciences. Where do you think the field is going? Where would you most like to see the investments and the focus to really reinforce the science that we need?
Well, certainly, I think the future is always the younger generation, and we're doing a lot of that to help promote that. And also, the diversity, obviously, in the field is very important. Also, from the International Astronomical Union, we are promoting that across the world. I mean, this is certainly an issue that goes across the world. But I think we need to, in terms of education, I mean, of course, education is the start of it all. And I think astronomy is a wonderful subject to draw in children at a very young age, to basically make them curious, to get them engaged sort of with the sciences, not to become an astronomer, but basically to get them interested in science. And in fact, there is actually one image there that I think tells a lot of the story, and that is actually also a way of getting both young and old engaged in this. And in fact, 30 years ago, earlier this year, we celebrated this famous image that was taken by Voyager 1. When it was already in the outer solar system, and Carl Sagan said, well, let's actually turn around and look back at our Earth. And this is the picture, the famous pale blue dots picture. That's us, that's home. I think that's one of the things that astronomy provides us, and space provides a lot of excitement, lots of inspiration, but also perspective, and maybe a little bit of modesty. I mean, we are this little speck out there. And also tolerance, because after all, we are all, to come back to my earlier quote, world citizens under the same beautiful sky.
Well, you have contributed so much to our understanding of this, and you're bringing science and art and brilliance and persuasion to it has made you a force to be reckoned with, and just a giant in the field. And it's been a delight listening to you and learning from you. And we look forward to your next discoveries and all of the young scientists that you've inspired and you've worked with, and who will be doing great things as well. So on behalf of the Kavli Foundation and Carnegie Science, I'm going to thank you again and turn it back over to Eric. And Ewine, it's just been a pure pleasure.
Well, thank you very much, Frank. It has been fantastic working with you and with the whole Kavli and Carnegie organization. Thank you so much.
Thank you. Eric?
Yeah, well, thank you, Ewine and Frank, for making us part of this really great conversation. It was really quite amazing. I want to again thank our co-hosts, the Kavli Foundation, the Royal Embassy of Norway, and the Norwegian Academy of Science and Letters for joining us to showcase such wonderful and exciting science and scientists. And of course, I want to thank the audience. It's no surprise that with Ewine's topic and her reputation, that we had such an amazing turnout, well over 600 people here. That's great, but even more interesting is the number of fascinating questions were asked. And like Frank said, we'll try to answer them, but really appreciate such deep engagement and such an exciting topic. I want to finish just by inviting everybody to join us again on November 10th, when one of our Carnegie staff scientists, Laura Wagner, is going to talk about her work on seismic time machines. She uses seismometers and she's been tracking, looking deep into the Earth to track what shaped the continents billions and hundreds of millions of years ago. So I hope you'll join us then. It'll be a fascinating talk. And as always, we appreciate your interest in Carnegie and Kavli, and we look forward to welcoming you back again soon. Until then, thanks, and have a nice evening.